So today I will start on continuous random variables, but before that I intend to do a few more problems. Uh, I yeah, so let me just start. Hmm, Okay, I need to consult the book before I can do this. Yeah, let us do this problem, section 3.7. Number 1. There are several subdivisions, and let us just do one by one. I will not discuss all of them, but just a few. So, to that expectation of ay plus bz given x is equal to, so this is together, okay? I don't like to put one more bracket. So, this is a times expectation of y given x plus b times expectation of z given x. Let us write down a few more properties. Uh, yeah, so I need to check this. Okay. So if y is bigger than or equal to 0, that is, it takes only non-negative values, then the same is true of y, x. Okay. And C expectation of 1. 1 means constant function 1, sort of as a random variable. So it's 1 omega, or indicator function of 1 omega. Anyway, this is equal to 1. And some more subdivisions are there. I'll just write, but maybe I won't have time to discuss every one of them. Yeah, this I will discuss. D, if x and y are independent, discrete random variables, then expectation of y given x. Yeah, let me see. This is equal to just expectation of y. That doesn't make sense. Uh, A little puzzled by this, but anyway, this is what the book writes. Let me write that. Let's see. Yeah.
Sir, what does the second point mean?
This one.
Yes, sir.
Sorry. Let me see. I probably didn't copy it properly.
Sir, it's greater than or equal to 0. The expectation is greater than or equal to 0.
Yeah, greater than or equal to 0. That makes sense because random variable bigger than or equal to 0 makes sense. So this is bigger than or equal to 0.
Okay.
Okay. Yeah. I think everything here makes sense. No problem. Even this makes sense as a constant function, random variable. This looks like a number, but it should be thought of as a random variable. Anyway, we will do it one by one very quickly. So, solution A. Okay. Yeah. So, expectation of, so you just have to, so expectation of See, you can use this. Hmm. Yeah, okay, let us just write this. I'm a little puzzled. Why is it that? Hmm. Okay. This is okay, fine, no problem. Okay, so just just write this. So you have to compute it for each value of z x. So you just compute this. If this is turning out okay, this is equal to expectation of. So what does this mean? This means that um, so the your uh, probability space has now shrunk to capital X being equal to small x. Okay, and mind you, this makes sense only if x is a value taken by x, meaning probability of capital X equals x is positive, and then so this is just a sum of the two random variables. So ax ay plus bz, given that x equals x, is the same thing as ay given x equals x plus bz given that x equals x. Okay, so so note, therefore you just write compute the expectations and they are the same. You have two random variables, I mean equality of two random variables ay plus bz given that x equals x is the same thing as expectation of the sum. Okay, that expectation being linear, you get something like this: a times expectation of, sorry, something just, okay, yeah, expectation of y given x equals x plus b times expectation of z given x equals x. But this is exactly the same thing as the other side. You can just compute it by sticking capital X equals x. Yeah. So this is same thing as, so therefore this is true for all x. So this is true for all x in the range of x. I don't write that full complete thing. Therefore expectation a is proved. Expectation of a y plus bz given x is the same thing as the random variable a times expectation of y given x plus b times expectation of z given x. Okay, so the main thing here is that these are random variables. We are not talking about equality of numbers. Even this is equality of random variables, not equality of numbers. Of course, it's a constant function, therefore this should be, yeah, this is not constant real number 1, but constant function 1 on omega. That's what it means. And for b, it is clear, right? So let's prove b. So since y is bigger than or equal to 0, uh, this f of y given x, yeah, f of y, let me write like this. F of y, this is what it means to say this is greater than or equal to 0. And so fy given x equals x. Okay, so this is not the way we write it, but we write the other way. Y given x. This is what is the meaning of this? This is a probability of something. Uh, yeah, so this, yeah, this is mass function anyway. This is, of course, bigger than or equal to y. But the important thing is y assumes value bigger than or equal to y. So this, okay, let me write it now that I started writing. This is y equals y, given that x. So this is not required. This is always true. What I wanted to say was y is bigger than or equal to y. Little y is bigger than or equal to for all y, for y in the image of y. And this is, of course, bigger than or equal to 0. Therefore, you just apply the definition. There's nothing to it. It's just very simple. Y given x equals x. Y given x equals x. This is equal to summation y times, yeah, fy x yx, yeah. But this factor is, of course, always positive, and this is positive because y is positive. So this is positive always, and this is positive, non-negative by hypothesis. And therefore the sum is bigger than or equal to 0. And that means what? You see, this is a random variable which is a function of x. Therefore, ey of x equal ey of ey given x is bigger than or equal to 0. You see, we should realize that these are all functions of x. Of course, they depend on y and z by the very definition, but these are random variables which are functions of capital X. Anyway, so this is obvious. And C is utterly trivial. I just leave it to you. It's always a constant function one. I mean, eventually, so the expectation, in fact, turns out to be, yeah, probability of, so you just compute it, it turns out to be equal to 1. That is absolutely trivial, except that this is, let me write just for clarity, 1 omega. Okay. And if x and y are independent, this is same as this, again thought of as a function. So if x comma y are independent, then so what do you know? F of y given x of this y given x, this is equal to probability of capital Y equals y, given that x equals x. So these two sets are independent, and therefore the probability is same as probability of y equals y. And now plug this into the equation. So expectation of y given x, y given x equals x. This is the function summation y. This is y, and then p of, so okay, let me write it one more step. Y given x, y given x of y given x, this is a way to write it, is equal to y. Yeah, so this is fy of y, but anyway, either way, just write this probability of capital Y equals y. and that is equal to expectation of y. So this is true for all x. Okay. So you see so you see your omega. Just let me draw a picture just for once. And first of all, x is a map to the real numbers. Or okay, it takes values in real numbers, but only discrete. I mean, countable set of values, whatever it is. So typical, if you take an x in here, and that's going to give you a slice of this. Okay, capital X equals x. And on each one of these, it returns the same value, same constant, which is independent of x. So you take another, so this may be x naught, maybe you have another. So you see this whole set omega is partitioned into subsets given by capital X equal to x, as x varies in the image of capital X. So, and when you do that, each time on each one of these sets, this is a constant Ey. Therefore, Ey given x is the constant function E of y. So here this is a constant function or constant random variable, whichever way you want to think of it. So this is equal to, if you like, Ey times the indicator function of omega. That's it. Okay, so it could be a bit confusing that on the one hand you have, on the one side you have a random variable, on the other side you have a function. So, sorry, you have a number. This number is to be interpreted as constant random variable. Okay. What else is there? I think there are two other sections, but I just leave it to you. I'm not going to discuss everything. Okay. I wanted to discuss some more, one or two more questions in this. Yes. So uniqueness. Uniqueness of conditional expectation, or what? Conditional random variable, conditional expectation. That's the way to say it. Suppose that and x is a discrete random variable, and phi x, psi x. Okay. Random variables such that for any well, let us, the book says suitable. I explain why he probably said that. Suitable function G we have. So you have this expectation of phi of x given x is equal to expectation of psi of x given x. Sorry. Here there is a given g of x. There's a g of x in here for any suitable function g of x. Then so in other words, this suitable here simply means that this makes sense. Okay, that's all it means. Then so the probability where this phi of x not equal to psi of x you see you have two random variables, y and z, let's call them. So y not equal to, probability that y not equal to z makes perfect sense. And that should be equal to 0. In other words, so this is, so phi of x and c of x agree almost everywhere. Where they don't agree is a set of set having, so agree almost always. Let me write like this: almost always. This is an expression that's often used. So almost always means that where they don't agree is something which has, whose probability is 0. Okay, yeah. So how do you do this? Yeah, so I can rewrite this. So let theta of x is equal to the difference phi of x minus psi of x. Okay. And now let us look at
Excuse me, sir. What is this function g of x?
g. G is some function, therefore from R to R. Okay. So therefore g of capital X makes sense.
So could you give an example? How, I mean, in a
So
situation?
for example, g of x could be x squared. Example, g of x could be x squared, g of x could be sin x, whatever it is. Well, I mean, so yeah, this is a type of things that can happen. See, x is, you have to think of x as a function from x to R, and g is another function. All function always means taking values in real numbers. Okay, notice that if x is discrete random variable, g is any function, then g of x is also a discrete random variable. Okay.
Okay, sir.
Yeah. So the idea is to take something like this, square of this, and then you take this random variable. Yeah, so let us take, so you are given that expectation of theta of x given g of x is equal to 0 for all g. Okay, g of x. So I claim that in this case, g, in this case, so how do you get this? This you get because you just uh, hmm, I'm taking square here. Hmm. No, let's not do this because I have square, whereas I cannot use that square there. Okay, let us take this and say what it gets. Okay, let us take just this. Okay, now I have to take, now I take G. Hmm. Hmm. Okay, yeah. So what do we know? Let us write this. Uh, Theta of x. Okay, yeah. So what are we given? So we have to give make use of the full hypothesis. The hypothesis implies that theta of x, here I am free to choose my g of x, okay, in a reasonable sense. And this is always 0. This is what I was told for all g, okay, essentially for all g. And now what I will do is, so let us look at some place where this is not equal to 0. So suppose that g of, theta of little x is, say, positive. It could be negative also. If it is negative, okay, let us say this is not equal to 0. Okay. Now I choose my g of x. So I have to choose my function, right? Constant function g. Choose g, choose g of x to be, choose g of, okay, g small x, first of all, for some x here. Okay, let me put here just in order not to, so put x naught here. Now choose g so that, so I want to write here, choose g so that g of x naught is equal to theta of x naught. I don't know if it will work, but let us just try this. Okay. Now compute and g of 0, otherwise it is 0. So, okay. This is actually, if x is equal to x naught and 0 otherwise. And now let us compute what is the function that we get. Okay. This should help us compute it. So what is expectation of uh, uh, theta x given g of x? So this we can compute, okay? And this should give us, so g of, we should compute this, what it is. This will make sense only if g of x naught. So, of course, see, this random variable is now a constant random variable. And at that, you see, you just apply the definition and you will get here, okay, let me write this. This is theta, so this is like y, right? So theta of x times, here you write f of y given g of x. And this can make sense only if x is equal to x naught. So here I have to have y is theta of x. Okay. So this is my y. And here I write, x, only x naught will matter, nothing else. Otherwise, this is itself, it makes no sense. This is only x naught. So this is probable. So this is equal to theta of x. You see, if this is equal to summation theta of x times, write this as probability that theta of x is equal to x naught. Okay, is equal to theta of x naught. So g of this is g of x naught, which is theta of x. Let me write here g of x naught. G of x equals x naught. So g of x naught, and that is theta of x. So here also it is x naught. So there is no sum now after this, because it assumes just one single value, and that's all you have. Okay, if you write sum here, it doesn't really matter. This will take care of it. So here, whatever it is, probability. So whatever it is some value, theta of x. So here it is theta of x naught. Okay, theta of x naught, doesn't matter. But what is this? On this side it is 0. No? And therefore, if this were positive, this should have been positive too. So seems to me that this is 0. This implies that theta of x naught is 0. If theta x naught is not equal to 0, see at x naught it does take the value theta of x naught. So this is going to be some, you see this is a discrete random variable, theta of x, and if it takes a certain value, then it probability of that is positive. This theta x anyway is positive, or theta x naught is not equal to 0. So this implies that theta x naught has to be 0. If theta x naught is non-zero, you get a contradiction. So seems to me that's all that is involved. Okay. Yeah, sorry, there's still one small thing. Just let me just think for a minute. Yeah, so what we showed was if theta of x naught is not equal to 0, then you, on the one hand, this is already 0, we know that. Okay, that's all. There is nothing more to say. That's it. It completes the proof. Okay. So I want to go to the next problem. There are some problems which I had marked, which I for discussion. Okay. So suppose that x1, x2, xn are independent random variables. Random variables. So let me just say what it is. Which are identically distributed. Okay. No negative integers. And independent of n. Okay.
Sir, can you scroll up, sir? Sir, no, sir, down, sir. Sir, so how did you go from the first line to second line?
You see, this takes only one value. You see, this, if you recall, conditional probability was defined P of y equals something, given that x equals x, makes no sense unless this has, this has possible, x is in the range, and my g of x takes only constant.
Okay, sir. Yeah.
Okay. So there is only one value that x can take. See, I forced it so that that value is same as this theta x naught value. Think about it. You see, if
Okay.
you want to say that theta x cannot take any value other than 0, suppose theta x, maybe it's a bit confusing. I could have just called it a or something instead of calling it theta x naught. Whatever value it takes, okay, you just put that and then compute this conditional expectation.
Okay, sir.
And that's all I have done. Okay, so here are independent random variables with mean, so identically distributed independent random variables with mean mu. Okay, and let n be a non-negative value. Okay, so be a random variable, n be a random number. Let us just say it that way, a random number. Okay, so random number while taking values 1, 2, 3, blah blah blah, and let Sn be the sum x1 plus blah 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 xn. Okay, so you see the sum depends on the value of n. Okay, if you change, so depending on this random, the value that this random variable n takes, this will change. Okay, so maybe I should write here Sn, just 1 second. Yeah, so let me write here. Okay. Yeah, I would like to write it as Sn. I don't know. Okay, let us just write it like this. S is a random variable which depends on both n and, I mean, okay, it depends on n, obviously. The value of n, rather. Okay, so S depends on several things, x1, x2, xn, and also the value of the random variable n. Now, what is the question? Question is, yeah, let me read the question. Show that expectation of S given n is equal to mu n, and compute expectation of S. I think that's what is asked. Yeah. Okay. So we can do this compute. So now this is actually, you just have to do this for each. So this is, mind you, a distribution. This is a random variable. S given n is a random variable and not a number. So you need to compute what its value is, what values it can take. That is by just computing the expectation of S given n equals n. So this is equal to, well, so you see, now this random variable, the number n is specified. So this is exactly the random variable sum of expectation of the sum. So xn, n equals n. That same thing as expectation of x1 plus blah 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 plus x little n, because capital N is equal to n, just plug in here. This is equal to n times mu. Each one is mu, and they are all independent identically. Independence doesn't play a role here, first of all. Identical distribution, that's what is important, because expectation is anyway additive. Okay, so this is what it is. And now the thing is, if you want to figure out what it is as a random variable, this is, first of all, you must write it as a function of n, and that n, so you see, it is the value of psi of capital N at the value n. Okay, so stare at this, look at this, this is a crucial part. It's very simple, but so psi of n is some some function, okay, whose value at n is actually, or rather I should say that, yeah, psi n of omega. So its value at omega is this. Yeah, which way, how does it? So this is some random variable whose value at n is, yeah, okay, that's the way to say it. When n, you plug in n, you get this n mu. Therefore, psi of n is equal to n mu. Okay, n times mu, or mu times n rather. Mu is a number, n is a random variable. So okay. So okay, now therefore, what is expectation of S? Now you apply this. Expectation of S is expectation of S given n, and that's equal to expectation of mu n. That's equal to mu times expectation of n. Okay. All right. So I have about half an hour. That's all I want to discuss about this conditional expectation. The next topic is actually sums of random variables. We have already discussed a bit of that, sums of random variables. But here, just let me recall for you the definition. If okay, if x and y are random variables or discrete random variables, then so z is equal to x plus y is the random variable, okay, whose mass function fz of z is, so this is just the probability that x plus y, z is equal to z. First write the definition. So we just have to write this formula for, derive a formula for this. Is equal to probability that x plus y is equal to z, and that is equal to, well, so you sum over x and y so that x plus y equals z. So there is a, it is understood that sum is over x and y, and z is constant, z is fixed here. So probability that x equals x and y equals y. So what we have done is, so this I hope you understand, this means and, okay. So what we have done is the set that z equal to z, this is because, so let me write that, since z equal to z, okay, as a set, subset of omega is union of the sets x equals x and y equals y. Allow x and y to vary arbitrarily, so the union is over x comma y, but subject to the constraint x plus y equal to z. That's it. Okay. And yeah, so once you understand this definition, we can straight away do some problems. There is not much to do this except to do problems. So I just directly go there. Maybe there are some examples worked out, but okay. Yeah. Let's do first problem. I hope you have been practicing some problems on your own. Otherwise, things are a little. Actually, the concepts are simple, but it can be very confusing unless you get a lot of practice. Okay. All right. So, yeah, the simplest example, suppose that x takes a value. Yeah. Values 1, 2, 3 up to n, m with uniform distribution. Uniform distribution or mass function. So it takes each value with equal probability. That's what it means. And y takes, so I'll just write 1, 2, 3 up to n uniformly. Okay. Find the mass function of x plus y. Okay. So here, so this, let us call this z. Let z is equal to x plus y. So you fix k. So you want to compute fz of k, that's equal to, just write the thing, I plus j equals k. So probability that x equals I, y equals j. And of course, I ranges from whatever, here to here, but constrained to this. Yeah, so xn, I forgot to give one important information. Otherwise, it's impossible to do this without this additional information. X and y are independent. I need to squeeze this in. Independent random variables. Okay. Yeah. So this means that, what does that mean? How does that help you? You see, this this tells you, this additional information tells you how the joint distribution function is. Okay. The joint distribution function is another exercise for you. So I write at the very end, if x and y are independent random variables, discrete, okay, discrete random variables which are independent, then their joint mass function fxy x comma y is simply fx of x times fy of y. This is absolutely trivial, you just think about it, okay? And in fact, the converse is also true, and this is an exercise. Do this exercise today itself. So this is a summation over I plus j equals k. And what is this? Probability of x equals I times probability of y equals j, because x and y are independent. Here is where you are using the hypothesis independent. And that's equal to what? Well, this is 1 by m, this is 1 by n. So 1 by mn times, well, summation over all possible ways of writing I plus j equals k. In how many ways can you write it? Mind you, I takes values from 1 to whatever, 1, 2, 3, 4 up to m. J takes values. So,
K minus 1.
yeah, so you can give arbitrary value for I, but not quite k minus 1, I'm afraid. You know, it's slightly subtle. Actually, minimum of,
So minimum of m, n, and k
yeah,
minus 1.
so minimum of k minus 1, and what is the other one? So m, yeah, this is it, I think. Mm. No, but m is always less than or equal to k. So, um, so, but okay. So this value of, yeah, k can be much smaller. So it depends on that value. Okay, that's it. And it should also, that should also be this n, I suppose, no? Because it cannot also exceed n. K minus 1 cannot also exceed n. We will assume that m is less than or equal to n. We can always,
So I can't exceed uh, n, I think. J can't exceed m, and both can't exceed k minus 1.
so
So the summation will be the minimum of will
so that is
iterate.
understood here. You know, see, you only allow for, so I didn't write the full value here, range of values. Why I don't need to care, because otherwise that value, when it is not attained, it is anyway 0. It is only when you try to write out, pin down the value. Here is where you need to really worry about. Here I don't need to worry about, but it's understood. See the number of, so let me write here, number of ways of breaking up. So this is equal to some number. It's really, I think it depends on value. So it depends on both m and n, a, m, n of k. And what is this function a, m, n of k? Number of ways in which you can write k as a sum of two numbers, two positive numbers. You see, if it was unrestricted, that would be k plus 1. I suppose, yeah, k minus 1. Hmm? Yeah, I am not allowing for 0, so k minus 1. But it is not unrestricted. So that is why we need to be a bit careful, but we cannot say anything beyond this, where, so you have to write this carefully. Amn, you understand what this function is? Amn of k is number of ways of writing k is equal to I plus j. Is that, I don't know if this is always so. This is definitely less than or equal to minimum, but whether it is equal to minimum of k minus 1 comma m, I think it will be. So anyway, k is less than or equal to, m plus n. Otherwise, it is 0 anyway, we know that. So if k is less than or equal to m plus n, yeah, I suppose it's okay. we will assume that m is smaller. Okay, we'll also assume that m is smaller compared to the 2. I don't know if it matters, but just to be on the safe side, assume that assume m is less than or equal to n. So the smaller one is less than or equal to that. Then there is absolutely no problem. I can write equal to minimum of m minus 1 and k. That's it. Yeah. So I go to the next page. Let us do some more problems. So sometimes this type of combinatorics very much enters into the picture. Okay, now I'll do 3. In 3, you are given the following thing. X and Y are independent geometric random variables with respective parameter alpha and beta. Okay, and then there's a formula. 3. Suppose that X and Y are independent random variables which are geometric with parameters alpha and beta. Oh, same problem. Find the mass function of. Actually, an expression is given in the book. Z equal to x plus y. I can write that, but let us just compute it. Okay, so the given expression is alpha beta by something. So here again, maybe one needs to assume, let me write here, alpha minus beta. So let's, I think it will take care of itself, but we'll just assume that alpha is bigger, okay? Alpha minus beta, 1 minus beta our mass function. So fz of z. So here minus z, 1 minus z, z minus 1. Minus 1 minus alpha power z minus 1. And we'll, so this is definitely alpha is not equal to beta. We have to assume that. And which one is smaller? Okay, yeah, alpha is strictly bigger than beta. Let's assume that. Okay. Actually, what is important is that alpha not equal to beta. Otherwise, this is negative and this is also negative. So it really doesn't matter, but let's assume that this is the case, okay? Given this. So recall, what is this geometric distribution? So fx of x is equal to, so there's a parameter alpha, no? So alpha is a parameter for success. So it's like saying you keep tossing a coin until head turns up with probability alpha. So probability of head equals alpha, and you until you meet with success, you keep tossing the coin. So this is 1 minus alpha power x minus 1, I think, times alpha. At the x time, you met with success. So this is the probability of that happening. And similarly, fy of y is equal to 1 minus beta power y minus 1 times beta. And now write the joint fxy of x comma y because of independence. So otherwise you will not be able to write this alpha beta 1 minus alpha power x minus 1 times 1 minus beta power y minus 1. Okay. And now it's clear what you need to do. Just compute fz of So Z, this is equal to sum over x plus y equals Z. Okay. And of course, x and y are all taking values where. So x goes from 1, 2, 3, etc. Y goes from 1, 2, 3. I don't need to write all those things. It's, when I say geometric distribution, it is understood. Okay, so this is equal to, yeah, so fxy, just write this condition first of x comma y. This is equal to summation alpha beta 1 minus alpha power x minus 1 times 1 minus beta power, well, z minus, so y minus 1, y is z minus x. Okay, so let me write that as z minus x minus 1. Okay. So here I can just sum from x is equal to 1 to z. Okay. Yeah. So this is so alpha beta. This is a, actually you see it's a geometric series because I can pull out this 1 minus beta power z minus 1, and here alpha beta had been taken out. Then what do I have? Summation x is equal to 1 to z. Okay. So I have here minus x minus 1. So I write here 1 minus alpha by 1 minus beta. Okay, because this minus x appears. So there's also an 1 minus alpha somewhere. So I'm making a mistake, I know, but divided by, so you see I'm pulling out, maybe it is better to just write here. I know, I just made some small, this needs a slight adjustment. Okay, when I write this x here and 1 minus beta here, I have taken care of this exponent properly. But this one, I think I should write here 1 minus alpha. And now you simplify this. This is a geometric series and it's almost there. You will get the correct answer when you do this. Is equal to alpha beta minus z power 1 minus beta power z minus 1, and then divided by 1 minus alpha is very much there. And this one, when you add up, so, okay, I think I will leave it, just stop here, but maybe state the next problem. Okay, do this as an exercise. Okay. So you will complete it, and I told you what the answer should be. It's very simple. Just you will get, it's just a geometric series. When you sum and then simplify, you should get this answer. Okay, now let me do the thing. State the next problem, and you will do it at home. So, which is exercise. Suppose that x1 blah 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 xr xn, yeah, xn are independent geometric distribution, geometric random variables, sorry, random variables with parameter same parameter P. Okay, so probability of success is P. Show that the distribution, so that the sum Z is equal to x1 plus x plus etc. xn is negative binomial. Binomial random variable. That's it. Okay. So compute this. Yeah. So negative binomial random variable. Okay. So it involves some. You see. How so? It's like asking how long do you have to wait before you meet with k successes when you repeatedly apply flip a coin, okay, indefinite number of times. So that is the negative binomial distribution. So probability of for any so it's like coin toss experiment where probability of head is some p, but I'm not sure whether it's the same parameter p. It may be the same parameter p. So try this at home. Okay. Yeah, I'll stop here for today. And the next lecture, I will start with continuous random variable. In between, there are some sections on random walk. I already discussed a bit of that very early on in the course. I'm not going to discuss that now. Later on, if there is time, we will return to Markov processes. At that time, I will discuss random walks. That's all for today. I stop sharing.